So let's start with the exercise number 1, where we are asked to sketch a transistor level schematic for a CMOS 4-input NOR gate. So the logic function would be y equals A or B or C or D whole bar, or we can also write this logic function as A or B or C or D in the parenthesis, and we can put some slash. So this slash indicates the function is complementary. So this is a Boolean equation, either this one or this one, and we know how to draw a transistor level schematic for this. So we see that there are 4 inputs. These are A, B, C, and D. So we start with the basic configuration of this would be, we have this pull-up network, and we also have this pull-down network. So we know that pull-up network is constituted or constructed by PMOS transistors, and pull-down network is constructed by NMOS network. So here we connect VDD, here we connect ground, and in the middle somewhere we have an output of this circuit. So the transistor level diagram would be, we know when we have to perform AND operations, so NMOS we take in series. When we have to perform OR operation, so NMOS we take in parallel. All right. And the complementary would be the PMOS for the AND operation would be in parallel, and PMOS for the OR operation would be in series. So remember this rule, and accordingly we start constructing. So we start with the 4 transistors because we have 4 inputs. And they're all connected in parallel. So here in the bottom, we have this logic 0, and they are shown to be connected in parallel, and their gates represent the corresponding inputs. So we have A, we have input B, we have input C, and we have input D here. Once we know that, we have formed the NMOS network, which is the pull-down circuit, we can then construct the OR. Let me try the different color so that it was easy to understand. So the 4 PMOS would be constructed like this. So as you can see them, and we know that the PMOS are going to form the top portion of this network, and these are same inputs A, B, C, and D. So here we have high logic, that is VDD. So this is pull up network, and that's your pull down network. The truth table for the NOR, let's say 2 input NOR logic, is simple. We have 2 inputs A and B, and there are 2 to the power 2, that is 4 input possible combination, 1 0 and 1 1. So what we see here, the output of a OR gate, for instance, would be if the any input is 1, the output would be 1. This is for the OR logic, right? But for the NOR logic, let's say NOR gate, so the output Y would be just a complementary of OR. So you see here, for any input combination, if any of the input of this logic is logic 1, the output would be logic 0. So we can try here. If let's say we have A is equal to 1 and B, C, and D are 0. So A is equal to 1 here, and B, C, and D is 0. So we know that this switch will get on. This switch will be open, open, and open. And all these switches will be closed, but this switch will be open. So there is no way output can connect to VDD. Rather, output will connect to the ground through the switch where input A is connected, right? So output will be pulled down to the logic 0 for the combination of this one. So this is how this circuit will perform the operation of NOR logic, and it is a 4-input NOR logic. Here is an example or exercise number 2 where we are asked to sketch a transistor level schematic for a compound CMOS logic gate for the following functions, where our 3 functions are given, A, B, and C. And what we understand from that, we have to form a compound CMOS logic. So when we talk about compound CMOS logic, it consists of PMOS and NMOS both, or we say that it's a CMOS logic. So let's start with exercise number 1. So we know that A, B, C, or D, and whenever we see this complementary bar, we can know that we just form the first the function without a complementary line with the NMOS network, and then just to complement it, we have the PMOS network. Let's start with this for the first function. So we have A, B, C. There are the 3 inputs right over here. C. Let me draw it a little down. And 3. So I have this A, B, and C. And there is an ORing of D with this AND network. So I see here, I have to put another switch which has input D. And now that's the total circuit that I see here. Once I form that network, what I can do, I take just a complementary, because 3 switches are in series here. So PMOS are gonna be in parallel. So you see here, I have A, B, and C, and they are forming a parallel combination. Now D was in series, D was in parallel with the ABC, so the D would come in series with this network. Right, and that's how this one. And here you have output Y, which is going to give you this function A, B, C, or D, and its complementary output. Here you have logic VDD or logic high. So we can verify the operation of this network by applying the corresponding combination of inputs. So that's the solution to exercise number 2, part A. Now let's talk about this exercise 2, part B. So the function given is A and B, or C and D right over here. You can see there A and B or C in the parenthesis and with the input D. So how to start with that? So again, I see here for the network B, A and B are in series. So I have this 2 switches, A and B. It is forming a parallel operation or ORing with another input, that is C. So here I am done with this, but I have another input, which is input D, which is in ANDing with this. So what I do, I draw another switch here with the input D, and that's a ground potential right here. Once I do that, I know now I have to take the complementary of it. So A and B are in series, the NMOS switches. What I can do, I can draw A and B to be in parallel for the PMOS. So A and B goes in parallel. Now the C is in parallel with A and B here, right here. So C comes in series with that. and the D was in series with the whole network. So D will be in parallel with this network. That is how I start creating this network. You see here, and this is the output Y of this boolean function or the transistorized circuit. I have a VDD here, and that is how I can realize this logic. So now we can see that I have third part, that is A, B or C, and it has an ending with another function A or B. So we keep on building this. Let's say how to realize this one. So let's first write this function, how this will look like. Let's erase this part, for example, to draw the function over here. So we are now drawing the network for the C part. So A and B are in series. So obviously I'll start with the NMOS. I can start with the PMOS also. So A and B in series for the NMOS. If I want to start with PMOS, I will draw A and B PMOS in parallel. So I can, and then I can take the complementary of it in the bottom part with the pull down NMOS network. So A and B, these are series, and there is an ORing of it with the input C. And once that is done, I see A or B comes in series with this. So I have two more switches, which are A. They are the same input, A and B. So here is my ground. So very simple. So I see Y is here. And now A and B are in series here. So I will start drawing A and B to be in parallel. This is A and B. Now C was in parallel with this. So C comes in series here. Let's say I have C over here. Now there is a OR function of A and B that comes in series with this above network. So I will draw A and B in series, and that will come in parallel with this network. So let's see how I draw it. So this is B, this is A, and that is forming a parallel combination of this one. So you see, I have finally formed this network right here. So this is how we can build or sketch a transistor level schematic for any CMOS compound logic gate, given that we have an understanding of how it is constructed. This is exercise number 3, where we are now asked to use a combination of CMOS gates represented by their symbols to generate the following function from A, B, and C. So we have 3 inputs, and how many gates we know so far is AND, OR, NAND, NOR, inverter, and the buffer. All right, so these are the functions we know. These are the logic gates we know, and their symbols we also know. So let's start with the A. So solution to the A would be, we have input A, and the logic gate symbol for this buffer would be Y equals to A. So this is how we can say that this is actually a buffer. For the B, we see here, this is a function, Boolean function of exclusive OR gate. So we assume that we can have complementary input available, A ending with B. That's the first gate. ORing of this would be done with A and its complementary B. So here is how we actually realize final function. So here we come with A bar B, here we come with A B bar, and the final function. This is OR gate, this is AND gate, this is AND gate. So it would be Y would be A bar B or A B bar. So you see now how we can actually construct this logic over here. What about these if these functions are not available, right? So what we do if the complementary input is not available, so we start with input A and input B, and we have to take the inverted logic of them. So here we have B bar, here we have A bar. So we start with first one, we want A bar B. So we have this A bar and the B, that's the first ANDing. And then we have AB bar. So here is another one. And then we can actually have the ORing of these two. So that's how we can also again realize the output. This is same circuitry, but we have to use two extra inverters here. So for the third logic, we see now we have Y equals to A bar B bar or AB. So again, we assume we have complementary inputs available. So we do that again. You have A bar, you have B bar. So that's first AND gate. Then you have uncomplemented inputs available. That's another AND gate. And with this, we see here, we have OR gate. So final output would be A bar, B bar, or A and B. Okay, and if we see that the fourth function, that is function D, right here, Y will be. So there are, we see here AB, then we have BC, and then we have AC. So this is how we see now we can actually construct these logic gates. So this is for the logic function T. All right, so that was all for this exercise session.